have 5 more minutes, to start the second talk, but even Henry isn't here yet.
And the next series
It is originally, to give a talk this afternoon, but Professor Henry really want to come to these sessions, and we allowed him to come here. And his talk is, the title of his talk is Recent Developments in the Catalyst Regenerations for the Beckmann Rearrangement of cyclohexanone, oxime to caprolactams. The authors are Dorhoff, Eichelberg, and Henry from the University of Technology Aachen, Germany. The speaker will be Henry.
Yeah, good morning, ladies and gentlemen. The title you read already, and when we speak about caprolactam, then we have to be aware of the following facts. Caprolactam is one of the major chemicals we produce. We produce about 4.4 million tons caprolactam per year, and it's one of the top 50 chemicals in the world. It's very interesting. We have a good return of investment of about 15% a year, and there is an annual growth between 4 and 5%. This expansion is mainly located in Asia because, or due to the demographical development. And therefore we read in the newspapers quite often announcement about new joint ventures in this field in China and Malaysia. And last November, finally Sumitomo announced that they have a 5,000 tons per year demonstration plant for a new caprolactam process, and that they are going to build a new world-scale plant in the next years, which will go on stream 2003. And our group is very happy that we could contribute to this development. And now, for what do we need caprolactam? Just a few examples. But the major need, the major demand is here, in this field. And now I would like to ask the girls of the audience if they are aware, when they put on in the morning these new stockings, or the nylons, or the pantyhoses, that they produced at the same time 50 grams of waste. Yeah? Did you consider that?
I only work fast.
Anyway, there's a problem starts. There's a problem starts. And caprolactam is mainly produced via cis conventional route, starting from benzene via cyclohexane, oxidation, and then the oximation of cyclohexanone in the presence of hydroxylamine and sulfuric acid, neutralization. The oxime is later on rearranged in hazardous oleum and to form caprolactam. The problem of this conventional route is the use of toxic substances such as hydroxylamine, the production of up to 4.5 tons of ammonium sulfate per ton of caprolactam, and also the use of corrosive substances such as sulfuric acid. Therefore, we have to develop a new route, and the new route starts also from benzene using the new technology of azide cyclohexene partial hydrogenation, then hydration to cyclohexanol. You should cancel this E. Afterwards, cyclohexanol, and then any technology to form the cyclohexanol of C. And in the last step, the Beckmann rearrangement using, let me say, now a ceride. And this route is much, much cleaner than the conventional route, and also we save quite a lot of energy in the first process, and it's also not as dangerous. This hydration dangerous as this oxidation of cyclohexane. Furthermore, we avoid completely the formation of the sulfuric acid and the use of sulfuric acid and the formation of ammonium sulfate. We had a big program to develop that process in our group, and that is shown here. We have done quite an extensive screening of different catalysts, and we studied that mainly in a fixed bed reactor, but then we realized that we needed a fluidized bed reactor, so we built up a single bed fluidized bed and also a fluidized bed with continuous regeneration. That means a system similar to an FCC unit. Then we studied particle size and attrition, we studied regeneration, and we studied also the evaporation of the oxide. Now let me just give you a few insights to our fluidized bed with continuous regeneration. We have here the reactor, then a conveying system for the spec catalyst, the regenerator, and then we go back with the regenerating catalyst. In reality, it looks like that, as shown here. We have the reactor, and that is the regenerator and the conveying systems, and the whole mini plant in our technical plant looks like that. Okay, and now I learned something out of the lectures this morning. We have to bring intermediate conclusions, yeah, to keep people away. Okay, so we can say as an intermediate conclusion, we have a new caprolactam process via the Beckmann Rearrangement. We have a reactor and process design fulfilled, and this is a fluidized bed with continuous regeneration. The selectivity we obtain in this fluidized bed with continuous regeneration is 97 to 98% at 100% conversion. We tested the catalyst for 1 year and 3 months and could we couldn't observe any long-term deactivation. Furthermore, we have done a lot of characterization work, and we studied the catalyst very extensively. We found that the reaction occurs at the outer surface and at the pore mouth, and furthermore, we also characterized the active sites, and the active sites are ethanol, silanol groups, and silanol-less. That means extremely weakly acidic sites. The reason for that I don't want to go in detail now, but you can come to the Catalysis Club tomorrow evening in Philadelphia, then you will hear that. Okay, now today I will, that's the reason why I'm here, I will focus more on the deactivation of the catalyst and on the regeneration of the catalyst. And we looked at the boron MFI catalyst, that is our precursor of catalyst, and we looked at that on different activity levels, and we have taken SIMS depth profiles. And so we looked at the fresh catalyst, at the spent catalyst with a residual activity of 30%, and after that we looked at the catalyst when it was regenerated, oxidative regeneration. And what we found in the fresh catalyst that the boron content was equal, and also the silicon content when we go from the outer surface to the inner part of the zeolitic particles. After the deactivation, we realized that the outer surface was covered by hydrocarbons. And that means if the reaction or the deactivation takes place at the outer surface, then the reaction has also to take place there. That was one of the conclusions. We have some other evidence. After the regeneration, we observed again the same boron content and the same silicon content at the outer surface as at the fresh catalyst. Furthermore, we found that by XPS investigation that these carbonaceous deposits consist of aliphatic hydrocarbons, not of aromatic hydrocarbons. That's very important, and you should keep that in mind. And you see here, you have the erosion time, the binding energies, and the hydrocarbon deposits are at the outer surface. Okay. In one of our first investigations, we looked, can we regenerate the catalyst? And so we have done that in a fixed bed reactor. Once a reaction during the day, we got this conversion and this selectivity, and in the night we regenerated at 500 degrees 1 bar in an airstream for 16 hours. Next day we have done the same, and we carried out that for 14 days. Every day reaction, in the night regeneration. So the catalyst, as you can see, is regenerable because after the 40th day we still get high conversion and high selectivity. So catalyst is regenerable. However, the question was, is that really the optimum for the regeneration? Or do we need other temperatures, other pressure, other time for the regeneration? Because even after the 40 days, we couldn't say if there, or we couldn't make a decision about the long-term deactivation of the catalyst. So we considered that, and therefore we carried out a kinetic analysis based on thermogravimetric data. I think I lost something. Such investigation based on thermodynamic data have been already done, or such approaches have been done in the past for the thermal cracking of polymers and also for the description of the reactivation of a spent catalyst which was used in the alkylation of benzene with todosine in the presence of HY. And Doyle and Tubes, they developed now a kinetic model based on the oxidation of a solid to a gas, then kinetic, Arrhenius equation, and also the temperature independence of the time of the regeneration. We used that model, and by the end of the day we had the regeneration time as a function of temperatures for different regeneration rates. As you can see here, when we want to have some regional activity bags, that we can work either at 600, let's say 80 degrees Kelvin, 80 Kelvin, 680 kelvins for 20 hours, or we can do it at 820 Kelvin for about 5 hours. I tell you, we didn't want to have some regional activity back later on in our unit. We adjusted the activity, let's say around 75 to 99. Yeah? Okay, anywhere between. So, but what we also knew is that we shouldn't go higher with the temperature than 850 kelvins. Okay, we had that, and now we considered when we burn off this coal, and mainly we have about 3.9% of coal on the catalyst. When we burn that off, then we can clean it, the catalyst, at around 500 degrees. So 500 degrees is very nice. However, the problem is that we get a hotspot, and the intrinsic temperature at the catalyst is much, much higher than 500 degrees. And that could be that we destroy now at such high temperatures our active sites. And our active sites are very sensitive because we have these cyanol groups, regional bridged cyanol groups and such cyanol nests. And these groups are located, as you can see in the HDS here, at the outer surface. So we have to be really careful that we do not destroy these groups and that no water is coming off. Yeah? Okay. Therefore, we thought we have aliphatic deposits. Maybe we do not need oxygen to get rid of them. And what we have done, we used just nitrogen and purged a lot of nitrogen over the catalyst at a certain temperature of around 500 degrees. And we could see in the thermogravimetric analysis that we could get rid of these carbon deposits. And that the loss of the mass found in the TG under nitrogen was almost identical with the mass loss under oxidative conditions. So we can regenerate with nitrogen. And the data for the regenerated catalyst are shown here. When we found in our unit that 99% of conversion and 93% selectivity. And the same we found in the presence when we regenerate with oxygen. Okay, regeneration with nitrogen is possible. Therefore, we propose now another, not only our unit with fluidized bed and continuous regeneration, we propose now another production plant consisting out of the reactor, then a regenerator for nitrogen regeneration. Okay, in the lab it was okay, just with nitrogen, but you do not know how it will be later in a big plant, if you can do it also in a big plant. Therefore we have also air regenerator. Okay, now to the next conclusion. We have been able to find a model and to determine the necessary residence time of the deactivated catalyst in the fluidized bed, in the regenerator of this fluidized bed system with continuous regeneration. And that enables us not only to find the optimum regeneration conditions, it enables us also that we can determine the volume of our regenerator. Yeah? If we need a big volume of the regenerator or a small volume of the regenerator. That was possible. Furthermore, we could demonstrate that we can use, instead of oxygen, we can use nitrogen for the regeneration. And that prevents hotspots and that avoids irreversible deactivation of the catalyst. I mean, the long-term deactivation of the catalyst. With that, I like to thank to co-workers, that is Mr. Dahlhoff, he worked in that field, and Mr. Heidelberg, both have done this. That is Mr. Vegas and Swesny, they worked on other fields, and also Mr. Rösler, Dr. Rösler, and Dr. Heitmann, they worked on this project. So I don't want to say wasted, but 6 people have been working in this field, yeah, and so Heidelberg and Swesny and Vegas, they are still with me, and I'm very grateful to them, and I thank you for your kind attention.
Now it's open for discussions.
I like it very much. You start from a fluid bed concept, you go all the way to process development, you come to surprising conclusions, and then you should go back, of course. So the question now is a fluid bed, is that a good idea? Because you have found the regeneration different than you had thought. So perhaps you cannot go back, and you might even turn around the things again. What do you think of that?
Hey, certainly, Jakob, we learned quite a lot out of that. And with this regeneration in nitrogen, yeah, gives us much more ideas than I told you here.
Yeah, I expect.
And I can assure you that the patents are written with the new reactor concepts and so on. But I cannot speak about that.
That's logical.
Yeah. But it's much, much simpler now. Because, as you know, in a fluidized bed with continuous regeneration, you have to be aware all the time that no oxygen comes to the reactor system. And so with that system, you can play quite a nice game. Sure.
You could make a simpler problem.
But maybe you have even better ideas than I do. Okay, also I forgot to say, I have to thanks to Sumitomo and in particular to Ishihashi and his group. With them we work together. Yes. So that's just came in my mind.
Yeah, I just would like to know a little bit more about your nitrogen regeneration. Are you actually volatile? Is this a volatilization step or what is the chemistry?
Oh, I mentioned to you that the deposits are aliphatic oligomers, and they are normally formed by the ring opening of the oxime, and you form first the cyanopentene, yeah, you make the ring opening, but then not the ring closure to caprolactam. You have the hydroxy acid amide, and then you have a dehydration, and that forms these linear cyanonitriles, and they oligomerize 2, 3, 4, yeah. But these are volatile compounds; they can get off, yeah, after a certain time. Temperature, you make just a desorption of them, yeah, from the surface, and you do not have, then as I showed you in the thermogravimetric picture, you do not have coke anymore on the outer surface. You have a
Carbon is not removed by CO2.
Huh?
Carbon, coke is not removed by CO2. The surface.
No.
How, where can you get oxygen to,
I don't use oxygen, not at all.
and then how carbon can evaporate?
Oh, just evaporations of the, yes, the Americans say white coke, yes. These are linear aliphatic cokes which are not, have to be burned off. Waxes. Yeah, but it's not as long as such waxes of C40 or whatever, yeah. It's, you can remove it. It's just a question of adsorption, desorption. Yeah. Bernard?
Yes, but nevertheless, your process takes place for the regeneration at a relatively high temperature. So there is a risk of some dehydrogenation of the oligomer. So did you consider the possibility to add some washing with a solvent to that?
Okay, we have also water in the system, yeah. And so you do not have to be afraid. You're right, at 500 degrees, you can dehydroxylate also such species. But if you have water present, it's not the case. And, but that is much, much better than in the case when we have oxidative.
No doubt about that. It's
Okay.
for
But you are right, it could happen, but we have also water present in the system.
Other questions?
Something about the energy balance. The older process used to have a reactive distillation column, oxide.
What's the older process?
The Dutch process, for example. The factories have this type of reactive distillation columns. Do you think your process will consume less energy than this type of distillation columns?
I didn't get your question, sorry.
Okay. So you have proposed a new route
Yes.
for this. There are two steps which is different from the older step.
Right.
The older has liquid phase oxidation for production of cyclohexanone.
Right.
Here you use steam for that. You don't
Yeah.
use oxidation.
We
This
do not
has
use
a-
oxidation anymore, or
don't.
shouldn't be used in the future. It's just a hydration of the cyclohexene, and that's in the liquid phase.
Yeah, that's the first phase. Then the
It's not a gas phase, it's liquid phase.
liquid phase.
120 degrees.
Okay. Previously it used to be 170 degrees, and they use air for liquid oxidation. It's manganese type catalyst. This is what I made you remember.
Yeah.
The problem there was, again, the separation of energy. When it's cyclohexanone, you need a lot of energy. So some energy was required for the reactor to do this. That first part. The second part was the oxime, the reaction, caprolactum reaction, was done normally in a large reactive distillation column. That is again an energy problem.
Maybe we should discuss it a little bit later outside to go deeper
So I was
into
just wondering,
details. I didn't
energy
get
balances of
all
the
your
process.
points.
The basic question is, did you do an energy balance?
Oh, the energy balance is much, much better because you do not consume so much hydrogen as in the case of the old technology. You do not go from benzene to cyclohexane. You go only to cyclohexene. That means 1 mole hydrogen less. And furthermore, the oxidation, as you know, from cyclohexane to cyclohexanone, the K mixture, yeah, is on a low conversion level. That means only 5 to 6%. So you have to separate quite a bit, and you have, which is very costly, to recycle about 95% of your cyclohexane, yeah, and compression and so on. In addition to that, you are working in the flammable area, and it costs also energy to avoid any harmful explosions. Yeah? So you are completely away from that. And the energy balance is much, much better.